Hello, we are Group 4 and we are here to present our progress on LoveTI to the rescue, overcoming Leo's low-textured environment challenges with advanced feature matching. At first, let me briefly explain what we are going to do. SLAM, or simultaneous localization and mapping, is a technology that enables a system, like a robot or vehicle, to create a map of an environment in real time, while simultaneously determining its own position within that environment. LeoSLAM is an advanced SLAM system that adopts the traditional ROM approach. It conducts feature extraction for every LiDAR frame to compute odometry. But in addition to this, it utilizes the IMU odometry value obtained through IMU integration and optimizes it using GraphSLAM, creating a map. There are many excellent papers on this topic. Our team decided to adopt the lightest weight and best performing SOTA paper, FastLeo, to replicate its method and further enhance its performance. The primary goal of FastLeo is to enable rapid SLAM processing in mobility systems equipped with lightweight computers such as UAVs. Let's look at the system overview. The process involves updating IMU and compensating for LiDAR motion distortion using a dynamic model. Distortion collected LiDAR points are obtained. Feature matching is performed through residual computation using a KD3 and distances. Optimization is done with the iterated error state Kalman filter, enhancing computational speed. The precise odometry obtained is then used to update the map. However, FastLeo has limitations that feature extraction performance is highly dependent on the environment. The video above shows an experiment using FastLeo to generate a map from sensor data obtained from a car driving over a bridge and tunnel. As you can see, the system is obtaining inaccurate driving directions for both data. Due to vulnerability of feature matching in FastLeo, a solution was introduced in FastLeo 2. Instead of traditional feature extraction and residual computation, FastLeo 2 utilizes an enhanced incremental KD3 data structure, addressing issues associated with feature extraction sensitivity to the environment. This modification aims to create a more robust model, especially in low-textured environments and with varying LiDAR performance. However, it also has disadvantages. First, KD3s are efficient only for nearest neighbor searches, not suitable for range queries or other types of searches. Second, the performance of KD3 can be sensitive to the order in which data points are inserted.
Now I will explain our approaches. Our approach involves leveraging the FastLeo model but replacing the feature matching component with a method called LoveTR based on detector-free local feature matching with transformers. Although I will explain it in more detail in later slide, we expected it to be produce dense match in low texture area and better than any other feature matching algorithms. As I mentioned earlier, LoveTR incorporates a tension mechanism in its transformer-based architecture, enhancing robustness. It generates high-quality matches even in challenging conditions, such as indistinctive region with low texture, motion blur, or repetitive pattern. However, the problem arises when we apply LoveTR for LiDAR point cloud. Since it only supports 2D images, it doesn't align with our objective. So we plan to convert 3D LiDAR point cloud data into 2D range images for feature matching. So I will address the solution we have devised to tackle the previously mentioned challenges. In our process, transforming 3D LiDAR point cloud data into 2D range images is key step, enhancing our ability to work with data effectively. After successful conversion, We proceed the feature matching, where we identify and match key features in the two images. This transformation enables us to leverage the capability of LoftR and achieve our goals. Following feature extraction, matched points in the 2D space are recovered into 3D LiDAR point cloud.
In this part, I will explain in depth of the implementation for our approach. We applied LoftR to Sejong 01 data, conducting feature matching with indoor weights. However, a key challenge arose from the mismatch between model input size and image size, leading to suboptimal results in feature matching. We addressed this issue by resizing our images, resulting in improved feature matching outcomes. We thought after correcting this issue, it would go on smoothly, but then we bumped into another one. When using Oster 128 with a resolution set to 2048 by 128, as you can see in this video, feature matching was accurate. However, the FPS, which is frame per second, was too low, measuring 3.6. Applying LoftR to low-resolution data using Oster 64 resulted in a decrease in feature matching accuracy with a slight increase in FPS to 8.6. However, this is still very low. Since the LiDAR's frame per second is 10, we couldn't apply it to FastLeo. Here are some reasons we found out that caused the low FPS. First, the machine we used for experiment was low performance. Spec of GPU was NVIDIA 2080 Ti, in which we believe a more powerful GPU could lead to a better result. Also, because the LoftR's architecture is based on the transformer, due to its innate nature, it exhibits a relatively slower processing speed in image-related tasks. To sum up, since the FastLeo is designed for machines with limited computing power, the slow processing speed of LoftR is not well suited. So, we decided to use SuperPoint instead of using LoftR. SuperPoint is a key point detection and description model which is based on the CNN architecture, which enables it to be efficient and lightweight compared to LoftR. So by applying SuperPoint, we successfully extracted 3D feature points. And the last step is to incorporate those into FastLeo. In obtaining odometry, we performed ICP using the differences in feature matching points between the current frame and the previous frame. Consequently, in order to obtain corrected odometry, we fed the derived odometry and inertial odometry to the iterative common filter of the FastLeo. In this section, I will explain about the results of our experiment. Before we share our results, I will briefly talk about the experiment dataset. We had two datasets for each tonal and bridge, and their trajectory lengths is shown in this table. This is the demo video using bridge data. The left video is obtained by the original FastLeo on bridge data, while the right video is obtained by our improved FastLeo. In these videos, they show odometry, while the left shows the inaccurate results on low textured environment. Our approach shows a robust result. It goes straight. The same applies for the tonal data. We obtain the same result, while the left one does not publish any odometry. Improved FastLeo, which is ours, can get right results. We use the EVO package to calculate the differences between ground truth trajectory and our trajectory based on our derived odometry. These graphs show the trajectory for the bridge for both our approach and original one. As you can see, the results obtained from our approach is aligned much more with the ground truth compared with the original Vestilio. This slide shows the trajectory for the tunnel. The results aligned with the output from the using bridge data. The results obtained from our approach is aligned much more with the ground truth compared with the original Vestilio. To conclude our project, we did the following things. First, we successfully implemented LoveTR and applied it to a Vestilio. After finding out that LoveTR showed poor performance, we quickly proposed Superpoint as a viable alternative. Finally, our model demonstrated superior performance compared to the existing Vestilio.